-1 to 0. -1 to 0. -1 to 0, we should be going up. So like from here to here, we're going up, right? And then also from 1 to infinity. So from here to infinity, we're going up. Good, right? That checks. Down, you check the down, it goes down. Local max at 0, 3, 0, 3, local max. Local minimum at these two, here and here. We're good. Yeah? So the good news, I hope you see that you would agree that the good news is that this is pretty like systematic, like there's a process to this and you get it done. The bad news is that that function's way too easy, right? The derivative was too easy, setting it equal to 0 was too easy. Not too easy, but relative to the other problems in the book, this is why this is like one of the first ones. Just want to get the process down. Yes? On your graphing calculator? Absolutely. Yes. On the test, I will, of course, expect to see your work, right? But you can always use your calculator as a tool to check to see if you're getting it right. And, you know, real world, you would never graph that polynomial by hand. You would always use a computer to graph it for you. But the things that are trying to be taught here is the connection between the derivative and the function. The derivative tells you if your function is going up or down. And from that, you can determine highest and lowest values of any function. It's pretty amazing. This works for not just for polynomials, this works for anything. Let's look at now the second derivative. Now this one always confuses, not confuses, but this is like, this is not as natural as the first derivative is. When we have this function, something like that, the first derivative is pretty obvious since it's the slope. It tells you where you're going up and where you're going down, right? Positive derivative, negative derivative, positive derivative. But what about the second derivative? Does the second derivative tell you anything? And it turns out it does. The second derivative tells you, well, it's very difficult to explain it. So let me see if I can try and illustrate it. Here we go. I'll do it with this. All right. So I want you to look at this. Does the green and red, can you all see the green and red okay on there? This is where the green and red switch. This is where the green and red switch. Here's another place where they switch. Do those points have anything to do with increasing and decreasing? No, they do not appear to be where the function is switching from going up to down, right? Do you all agree with that? Like here I'm going up, 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 down, 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 down. And then it's switching, what's switching? And then over here, down, 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 down. I'm switching, down, 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 and I switch there. So what is it about those color switches? What is it in the graph that's switching? It does actually have to do with how fast the slope is increasing. Yes, it does.
But it doesn't line up exactly.
Okay, so the second derivative, what is it about, right? That's what I'm trying to lead us into here. The first derivative is all about what?
Slope of the tangent line.
Yes, but from what we're talking about today, first derivative somehow connects increasing and decreasing, right? Increasing and decreasing. Second derivative is called the concavity of a function. Concavity. Concavity. Think about that word.
So you're switching from the parabola to the fractional? And then
Wait, switching from the what?
From the upside down parabola to the fractional?
Okay, so you're almost seeing like this is like part of a parabola,
Yeah, that's one.
and then you're saying it's switching to what?
To the fraction?
What do you mean fraction? I think you're on the right track.
The ration function that looks like that?
You're on the right track. I think you're trying too hard though. Look, this one looks like a parabola that opens down, and this green part looks like
Is that an exponential?
part of a parabola that opens up, and then this one looks like it's switched over to a parabola that's opening down, and then it's back to a parabola that's opening up. But concavity is not really a parabola. That's what it looks like in this picture. But concavity has to do with concave. That's where that word comes from, concave. And a function is either going to be concave up or concave down. A smile or a frown, right? Smile, frown. Right? That's what you have here. This red looks like a frown, right? It's been cut off, but that looks like a frown. Agreed? This green part just looks like part of a smile. Yes? And then now part of a frown. And then part of a smile again. Yes? Concave down, concave up, concave down, concave up. What determines whether or not you're going to be concave down or concave up is the second derivative. What do you think concave down is going to come from? The second derivative being what? It's either positive or negative, right? What do you think? Fortunately for us, it works out the way you would think about it. This concave down is like a frown, right? Frown people. People who frown are really what? Positive people? No. Right? They're negative, right? So fortunately it works out that way. Happy people are positive people. Second derivative positive. Second derivative negative. Second derivative negative, positive, negative, positive. These points are where the second derivative is what? Changing from negative to positive. If you change from negative to positive, you have to go through what number? 0. So these points right here are where you're actually changing concavity. That's where your second derivative is negative. 0. Go with me? Okay. So first derivative is all about up and down. Second derivative is all about smiles and frowns. That's what it's about. Concave up and concave down.
What's the purpose of finding the second derivative?
Okay, so what is the value of the second derivative in these concave things, right? Well, one, we can use them to help us sketch functions. Even if the functions are not polynomials, we can use them to sketch. But there are other applications, like in business problems. Let's see. Let me draw a function for you here. Let's say we're a company and we're looking at our profit for the last year, right? And let's stop. It doesn't have to stop, but let's just stop this here. If we're looking at our profit for the last year, we're pretty happy, aren't we? Profit was increasing the whole time. The whole year the profit was increasing, right? The whole year. And let's say we broke this into months or something, or days. Then the first derivative of this function is always greater than 0. Yes? Always greater than 0. What about the second derivative though? Do you see a change in concavity in there? Yes? The change in concavity is somewhere where it looks like this smile turned into a frown, didn't it? It's where the two edges of the smile and frown came together, which is, you tell me where. Tell me when to stop. Somewhere in here? Okay, this would be it right here. This is known as an inflection point. That's what we're going to call it. That's its technical name. But from a business perspective, that point is important to me. And here's why. Right here, at any point, my profit is increasing, isn't it? Because the slope of tangent line. So notice what's happening here. I go up, go up, go up. My profit is increasing, right? To the right of this point, is my profit still increasing? Yes, but it what? It slows down. My profit is not as steep, is it? This point in business is called the point of diminishing return. It's the point at which you're still getting return, but it's diminishing as you're going. So what we would look at in a business model is we'd say, wait a minute, what happened there? We hired that guy. We hired that guy. And we're still making money, but it's slowed down. Something, he's plugging up the system, right? Something's going on. That's an important point, because you don't want your business model to look like that, right? You want it to do, you want your profits to continue to increase. You don't want to ever get the concave down. Does that make sense? But it sure as hell is better than this, right? You don't want it to do that, because then you start having negative slope. That's a different story. So the second derivative is important in depending on what the application is. You could change this to time and temperature, then you'd have the same sort of discussions. All right, so we can go through, and I can go through the notes, which I'm not going to, and we can sit there and talk about, okay, concave up, concave down, blah, blah, blah. But I think what we'll do is, let's take that example we just did, where we found where it went up and down, and we found the max and min. This time I want to talk about its concavity. So the original function was x to the fourth minus 2x squared plus 3. Am I remembering that correctly? Yes, okay. So we already figured out where that function is going up and down. We've found where its local max and local mins were. We're good. Now let's look at, I want to know this. Where is f concave up? Where is f concave down? And then I also want you to find the inflection points. I know it's 2:20 and we all want to get out of here. I know it's the day after Halloween. But please pay attention to what I'm about to say. For what we just did a second ago, we took the derivative, we found its critical numbers, right? We drew those numbers on a line, we picked some test points. From that we could tell where the function was going up and down, and then we could say where the max and mins happened, right? We're going to do the exact same thing that we just did, but instead of using the first derivative, the second derivative. We're going to do same thing, critical numbers. We're going to draw a number line. We're going to test points. But instead of that telling us about up and down of the original function, it's going to tell us about smiles and frowns. So the function we're going to work with is going to be different. It's going to be a second derivative. And then the results of our testing are concavity instead of up and down. But it's the same process. That kind of makes sense? Let's do it. I need the second derivative. We already had the first derivative, didn't we? So the second derivative would be okay, 12x squared minus 4? Yeah. That's it. Everyone agree? That's the second derivative. All right. Well, at least that's not that bad. Let's take this second derivative and set it equal to 0. So second derivative instead of first, which would be 12x squared minus 4 equals 0. You could factor out a 4. You could divide both sides by 4. This is going to be, I hope, a pretty clean thing to solve. I'll divide everything by 4. I'll move 1 over to the right. I'll divide by 3. I'll square root it and do plus or minus. And just so I have an idea of where those are, let's go ahead and do that on our calculator. So do 1/3, take the square root. Approximately plus or minus 0.577. Anyone else get that? All right, so those are two critical numbers. We also need to check if the second derivative doesn't exist. And it does. It's a polynomial, right? This is a nice function. No worries. So once I'm here, what do I do? How do you mean? What do you mean?
Like put that into the second derivative.
No, not yet. Not yet.
Click one out.
So at that,
I don't have an interval.
so at
Number line. Number line's next. Get used to this. This is what's going to take these problems. This is what's going to take forever with these problems. Number line, you put your two critical numbers. Negative root 1/3 and positive root 1/3. And I'm going to box those because those are my critical numbers. I'm going to use those to partition my number line into how many regions? That only creates 3 regions, right? So I only need to pick 3 test points. Those test points can be anywhere as long as they're not on those numbers. And negative 1's a good one. 0's a great one. And 1. And where are these points that I just picked getting plugged into? Into the second derivative. Into the second derivative, because the second derivative tells me whether or not I'm smiling or frowning. So that's where I'm going to plug them in. So let's go f double prime of negative 1. I'm going to plug that one in. F double prime of negative 1 equals 8. Which all I care about is the fact that it's positive, right? And because it's positive, what's this?
smiling,
What is smiling?
the line,
What's concave up? No, not the second derivative. Not the first derivative. The original function. That means the original function is smiling. The original function is smiling because the second derivative is happy, right? Well, sorry. The second derivative is positive, which makes the original function happy, I guess. Plug in 0, what do you get?
Negative 4.
-4. Oh, it's sad. So that means that the original function is down like that. And then at 1, you get 8 again, which means the original function is smiling.
So what happened at 0?
What happened at 0? Nothing.
We're down for a reason.
Yeah. So now, I would like to write out where, like answer the question, where's the function concave up? Where's the function concave down? That was the original question, right? I gave us this and I said, where's this function concave up? Where's it concave down? So where's it concave up? So f is concave up on the interval, what? Negative infinity to negative root 1/3. That's it. Union root 1/3 to infinity. So that's where it's up. Here to the left, here to the right. And then now for down, it's just negative root 1/3 to positive root 1/3. It's the stuff in the middle. Are we done? Inflection points. So inflection points, those occur when you have a change in concavity. You know how like with the first derivative, up to down meant max, down to up meant min? Here, any change in concavity means inflection point. Any change.
So the inflection points would be negative.
We're going to have 2 of them, right? Because we go from positive to negative and then from negative to positive. So we have an inflection point here and here. So we have two of them. So inflection points are going to be, well, we have to take negative root 1/3 and plug it into the original function. The original function. To actually find the point on the graph of the original function that gives us, that is the inflection point. So yeah, that sucks. You got to plug that in. All right, let's plug this in here. What is that to the 4th power? Well, what is this squared? The negative goes away. Root times root, gone? So you just get 1/3. That's if you squared it. But we're going to raise it to the 4th power, which means square it again. 1/9. 1/9. So we have 1/9 minus 2 times, and what was it squared again? 1/3. And then plus 3. So we get 1/9 minus 2/3 plus 3. Y'all following what I'm doing? Get a common denominator. 9, 1/9 minus 6/9 plus 27/9.
Gotta lay off the whiskey drinking.
So 22/9. 22/9 is where that's happening. I could write this as a point, couldn't I? This would be the point negative root 1/3 and then 22/9. That would be one inflection point. What would the other inflection point be?
Same thing.
Same thing, right? Because when I raise it to the 4th and square, I get the same thing. So I'm going to put a little plus here. Plus or minus that is still going to work out like this, and then I'm going to get plus or minus. So those are my two answers. It's positive root 3, root 1/3, 22/9, or negative root 1/3, 22/9.
And then you have to graph all that.
Well, no, this is it. We're done. We're done. But the next section after this section is called curve sketching. And can you see how now we're starting to build up? We're building up a lot of pieces to the graph now. Yes?
So the inflection points were found by putting
Our critical numbers for our second derivative into the original function. Now I want to bring back up that graph right here. And don't worry, we're going to go, okay? We're going to leave. Everyone, bring up that graph again. We had looked at this a second ago and we had all said we were happy with the fact that we found where it was increasing and decreasing and all that stuff, right? But what we just said we found was the inflections. Well, that didn't work. Trying to zoom in on this a little bit more. What was root 3? 1 over root 3. Sorry, 1/3 square root. Did we? What was it? Point what? 0.577? All right, both positive and negative. If I go to 0.577, which would be right around, I don't know, somewhere around here, and I go up on my graph, what was 22 over 9? Like 2 point something? Right there? Somewhere around there? And then I have another one on the other side. Right about there? Do you agree that that's where we change? Do you see the change in the graph? From the frown, from the smile to the frown, right here, oh, so sad. And then from here, smiling again. Okay. Your homework tonight is to start the homework from 4.3. I have assigned, what's in the schedule is assigned, this is page 222. You're supposed to do 4, 5, 7, and 8. That's what took me an hour and 20 minutes to do. I can tell you right now that if you start with number 4, it's a rational function. It's going to throw you right into the fire. You might want to do like number 1 first. It's another polynomial, just so you get the idea. If you feel comfortable with this, move into 4 or 5. 4 is a rational function, 5 is a trig function, 7 is exponential, and then 8 is both a combination of a polynomial and a logarithm. So it's kind of like, whoa, all of a sudden you go from this nice sweet function to something kind of crazy. All right. Then next class, we will finish it up. Yeah, so we have 3 days for the next 2 sections. That's what we have, 3 days for the next 2 sections.
Are they that long or hard?
Well, curve sketching there's a lot involved. Because when you think about it, what we've done in here now is we found max and min and all this. But now we can say, hey, go back to college algebra. Remember how to graph?
Yeah.
Find x-intercepts, symmetry, all these different things.
So basically we're just building up like a profile.
We have like a massive technique for sketching now. And it includes both the first and second derivatives.
Now, when we sketch, it's not so rough. It's actually
It'll be really nice. It'll be real, real good. But it'll take forever.